In the previous video, we counted the number of ways to arrange L indistinguishable objects and N indistinguishable objects in a row. This result will now help us to derive the binomial theorem. To motivate our derivation, we walk through a sequence of algebraic calculations that quickly becomes difficult to perform by hand. We know that we can expand the square of x plus y by writing two factors of x plus y and then distributively multiplying each term in the first pair of parentheses with the terms in the other pair of parentheses. The result collapses to x squared plus 2xy plus y squared. The cube of x plus y is the square of x plus y times another factor of x plus y, which simplifies to x cubed plus 3x squared y plus 3xy squared plus y cubed. The term x plus y quantity taken to the pth power is called a binomial because it contains a sum of a first term x and a second term y. What is the result of taking x plus y to perhaps very large powers p? Rather than relying on brute force calculations, we address this question by deriving a theorem as follows. There are p copies of x plus y. When the first x is multiplied against the second x, and then that product is multiplied against the third x, and so on, the resulting product is p copies of x. When, instead, the first y is multiplied against the second x, the third x, and so on, the resulting product is y times p minus 1 copies of x. If the first x is multiplied against the second y, and then this product is multiplied by the third x, the fourth x, and so on, we get x times y times p minus 2 copies of x. Notice that y multiplied by p minus 1 copies of x equals x times y times p minus 2 copies of x because multiplication is commutative. Hence, y times p minus 1 x's and x times y times p minus 2 x's are really two instances of the same quantity, p minus 1 copies of x times y. If p is large, there may indeed be many such terms to list. Depending on how many x's and how many y's are being arranged in a row, it may be difficult in some cases or easy in others to enumerate products. Even though we have used the gray ellipses to avoid writing out many products, we are assured that we have explicitly listed all the ways to arrange p copies of x. There's only one way. In contrast, we have not listed all the ways to arrange p minus 1 x's and the 1 y. There is only one way to arrange p copies of y. How many copies are there of terms with p minus 1 x's and 1 y? In other words, how many ways are there to arrange p minus 1 x's and 1 y in p slots? Using the formula L plus n factorial over L factorial n factorial from the previous section, we know that there are p minus 1 plus 1 factorial over p minus 1 factorial ways to arrange p minus 1 x's and 1 y in a row. The p factorial over p minus 1 factorial copies of terms that have p minus 1 x's and 1 copy of y add up to p factorial over p minus 1 factorial times x to the p minus 1 times y. Terms with other mixtures of x's and y's can likewise be collected. All of these terms can then be collected as the sum from k equals 0 to k equals p of p factorial over p minus k factorial times x to the p minus k times y to the k. This is the binomial theorem. One of the benefits of writing an expression in the form of a sum is that some terms become obviously negligible during practical application. For the binomial where x is replaced by 1 and y is replaced by the quantity delta y much smaller than 1, use the binomial theorem to show that 1 plus delta y quantity taken to the pth power is approximately 1 plus p times delta y. Use this approximation to calculate 1.1 taken to the 5th power and compare the approximate result with the exact answer. In this slide deck, we studied the number of permutations or ways in which we could arrange distinct objects in a row. We used factorials to organize our calculations. It turned out that the factorial was also useful for organizing calculations to determine the number of combinations or ways in which we could grab objects from a container. The result we obtained allowed us to derive the binomial theorem, which can be used to simplify calculations like the example in the previous slide and which will later be useful for calculating financial interest.